Just like any other Sunday, you and your friend, who works at a space research organization, were playing video games. He was explaining about their recent project, which was aimed at building a rocket that can travel with a speed of around 95% the speed of light. Suddenly, he got a call. His face was filled with excitement. He kept the joystick aside and told you that he has been called to the research center and he will return in a week. You felt bad that he left without completing the game. Losing interest in the game, you started listening to music. But something caught your attention. You went to the window and saw a rocket flying. The rocket was really fast, which reminded you of your friend's project. Now you are sure that your friend is inside the rocket. I have a question for you. Will you be waiting for him on the next Sunday? If I were you, I wouldn't. Hello everyone. In today's video, we shall be discussing the time dilation concept in special theory of relativity. Generally, when we talk about mechanics, we refer to classical mechanics. But when an object travels with a speed comparable to that of light, classical mechanics fails to explain its properties. That's where relativistic mechanics comes into picture. To completely understand time dilation, you need to comprehend the concepts of relative motion and electromagnetic waves. Let's start with relative motion. You must have heard about frame of reference, right? Here is another definition. It is a system of geometric axes in relation to which measurements of size, position, or motion can be made. A frame of reference consists of three-dimensional space and a clock. In simple words, frame of reference is just a perspective that you use to determine the behavior of an object. When you say that a vehicle is moving, you mean that it is moving with respect to the road. But if you see the bigger picture, Earth itself is moving around Sun at a speed of 30 km per second. So, it is safe to say that motion of an object is always expressed relative to a reference frame. Now let's try to understand inertial reference frame. In this reference frame, Newton's first law of motion is not violated. That is, in this reference frame, an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. To put it simply, we can just say that inertial frame of reference is either at rest or is moving with a constant velocity. Even if Earth is orbiting Sun at a constant velocity, there is a centripetal force acting on it. So, some books give a straightforward answer no, that Earth is not an inertial frame of reference. Still, it all depends on the reference frame you are considering. If you say that Earth is an inertial frame of reference, you have to mention with respect to what. Similarly, if you are saying that Earth is not an inertial frame of reference, you have to again mention with respect to what. But for this concept, it is safe to assume that Earth is an inertial frame of reference. To get a better understanding of relative motion, let's take a look at some scenarios from different inertial frames. In this case, the human perceives the velocity of the car to be 80 km per hour because the car is moving at 80 km per hour with respect to the road, whereas the human is at rest with respect to the road. In this case, the person inside the car is at rest with respect to the car. In fact, he perceives the surroundings to be going backwards with the speed of 80 km per hour. In this case, the human perceives the velocity of the white car to be 60 km per hour and the yellow car to be 80 km per hour because they are moving at that certain velocities with respect to the road and the human is at rest with respect to the road. But if you look at the same scenario from the perspective of the white car's driver, then he would perceive the velocity of the yellow car to be only 20 km per hour because he is already traveling at a speed of 60 km per hour and the difference is only 20 km per hour. Finally, if you look at this scenario from the perspective of the white car's driver, he would feel that the yellow car is approaching towards him with the speed of 140 km per hour because he is already traveling at a speed of 60 km per hour and the yellow car is coming in the opposite direction with 80 km per hour. Okay, now let's discuss about electromagnetic waves. Electromagnetic waves are composed of electric and magnetic fields. James Clerk Maxwell found out that speed of electromagnetic waves is constant in vacuum. It is equal to the product of its frequency and wavelength. The value of speed of electromagnetic waves is 2.99792458 into 10 to the power of 8 meter per second. Celeritas C is the Latin word meaning speed. Speed of electromagnetic waves in vacuum can also be expressed in terms of magnetic permeability of free space and electric permeability of free space. The speed of light in vacuum is always constant. If you are standing on earth, you will measure it to be c. If you are riding a car, you will measure it to be c. If you are inside a plane, you will still measure it to be c. Even if you are inside a rocket that travels at half the velocity of the speed of light, you will still measure the value of speed of light to be c. But we have just discussed that motion of an object is calculated with respect to a reference frame. Then how can the speed of light be the same in all the reference frames? To answer this question, let's conduct a thought experiment. Let's say that your friend is carrying this device in his rocket. There is a photon in this device that takes 1 second to go up and 1 second to come down. Now let's pretend that you can see this device from Earth. For your friend, the path taken by the photon is a straight line. It goes up and comes down, that's it. When you see it from Earth, you see that it moves along the direction of motion of the rocket. The path traveled by the photon would look somewhat like this as seen from Earth. Using Pythagoras theorem, we can find out the distance traveled by the photon. We know that speed is the distance traveled per unit time. From that, time is equal to distance by speed. Let's call the time experienced by the person inside the rocket as delta t naught. Then it will be equal to d by c, where c is the speed of light in vacuum. But for the person on Earth, it will be square root of d square plus l square by c, because the photon is traveling some extra distance. Now let's say that the rocket is moving with a velocity v. Then the horizontal distance traveled by the rocket L is equal to v times delta t, and d is equal to c times delta t naught. You can use basic algebra and plug in the values to get the final equation of time dilation. That is, delta t is equal to delta t naught by square root of 1 minus v square by c square, where delta t naught is called as proper time interval and delta t is called as dilated time interval. Dilated means expanded. The person on Earth will experience more time compared to the person on the rocket. The rocket in which your friend was traveling has a velocity of 95% of c. If you plug in the values into the equation, we get delta t is equal to delta t naught by square root of 1 minus 0.95 c square by c square. That finally gives us delta t is equal to 3.2 delta t naught. He said that he'll return in a week, but on Earth you'll experience 3.2 weeks. But wait, photons travel at the speed of light. So delta t is equal to delta t naught by square root of 1 minus v square by c square. Here v is equal to c, so it will be infinity. Mathematically speaking, a person needs to perceive infinite seconds for the photon to perceive 1 second. That is, there is no such thing as time for photons. If we see the world from the perspective of the white car's driver, then everything seems to be normal. But if we see the same world from the perspective of a photon, everything seems to be freezed. Again, if we see the world from the perspective of the person inside the pod, everything seems to be normal. But if we see it from the perspective of a photon, everything will be freezed. When you travel a long distance in a plane, you actually traveled a few nanoseconds forward in time with respect to a person who never boarded a plane.